some office in Belgium, in Waterloo. And today I want to take you some insights on maintenance 4.0. Normally, Marie Berlioz from Alstef, one of our customers, should be here, but unfortunately, she had some personal difficulties. So today I will present for Berger-Levrault and also the experience of Alstef Group on the path of maintenance 4.0. So few words of Berger-Levrault and with also Alstef Group. So Berger-Levrault is a software editor. We developed and market what we call CMMS, computerized maintenance management system, and also what we call enterprise asset management systems. We are a quite old company. We commercialize CMMS since 35 years, and we have a lot of customers all over the world. I would say more than 10,000 customers. We deliver 4 main products. So the CMMS system, CarSource, with 2 mobile apps, CarTouch and CarFlash, and of course, Berger-Predix, which is a platform, an IoT platform dedicated for maintenance. Alstef Group, our customer, is a French company. Alstef Group make some automated solution systems for logistics, and they also provide services with the systems. The services are for the operation or the exploitation of the automated logistics systems, but also the maintenance of the automated logistics systems. So Alstef produce logistics systems for many markets, baggage handling solution for airports, but also intra-logistics solutions and parcel sortation solutions. In this project, we are going to focus on assets on the airports, so on the baggage handling solutions. 2 parts in this presentation. For first part, we will speak about Berger-Predix, and after that, we will see how Alstef use Berger-Predix to optimize the maintenance and to optimize the asset performance. So let's start with Berger-Predix. Berger-Predix is a platform dedicated for maintenance. So it's an IoT platform with some EA algorithms and models dedicated to the maintenance. But before I want to explain you in which vision we designed Berger-Predix. In fact, as a CMMS solution provider, we think that CMMS will become a technical platform to combine, of course, management process. So the management process, which are managed in CMMS and enterprise asset management, but also to mix this data coming from management process with data coming from the field, data coming from the assets, and the use of artificial intelligence to automatically analyze, treat, and transform this data in some very useful or information or in some insight. Another thing, we could say that CMMS will evolve because actually we are in a digital age where there is a transformation, and this transformation is an overlay between the physical world and the digital world. And we think that in CMMS we are going to leave this overlay by the concept of digital twin. So the overlay between the reality of the asset on the field and the information that we have on these assets on the digital field. So this vision is not focused only on IoT. There is some other fields which are interesting in asset management and asset performance regarding to 3D view, but also the use of augmented reality, but also the use of some technique to optimize energy management and to go through sustainability. Today, we are going to focus on IoT and EA for CMMS systems and for maintenance, and we are going to focus on Berger-Levrault. So Berger-Levrault is like, I would say, all IoT platform made with some modules, some classical modules, so the ability to interoperate with the IoT, so with all the protocols, all the networks, all of the Internet of Things, the ability to also interoperate with connected machines, with field automation bus, and to gather all this data, all this big flow of data near real time, to store it with the big data concept, and of course to propose some models to convert this data, this raw data, in useful information for the maintenance process. And after that, to propose dashboard mixing to make some great analysis, or to have the ability to have some control process on the assets with this data. The specificity of Berger-Levrault is the use of some IoT technology and some rules engine and some artificial intelligence algorithm dedicated to maintenance. What you see in this slide is an architecture which is compliant with the new technological principles of the new digital age, the connectivity between people, assets, processes, and of course, existing IT systems like CMMS or enterprise asset management or other kind of management systems. Of course, the use of big data, but not only big data in a, I would say, in a classical view of the big data as a data lake with some batch flow and some business intelligence dashboards. No, in fact, it's a big data. We have to see it in this architecture as an ability to have a stream data flow, to be able to collect data in real time and to be able to analyze the data in real time. Of course, the use of API to consume and to analyze the data flow, and some business rules connected to the CMMS system. A focus on the modules and what is necessary to be able to go through the maintenance 4.0. First of all, we need to interoperate with the world of IoT and, of course, the world of existing protocols and, by the way, existing field bus automation. All these standards, there is a lot of standards that we can support. All these standards and all this configuration of the connectivity is managed by what we call a device management. So the device management helps you for each asset identified by a unique ID in the CMMS system or the enterprise asset management system. We can pair it in the device management with some sensors. We can define the technology and the protocol to use to collect the data coming from the sensor. And of course, we can pair this existing sensor on the field with the management objects that is represented in the CMMS and enterprise management. By doing this pairing, we are able to go direct to control the data flow directly from the sensor to the enterprise asset management system or the CMMS system. I will show you after some example what we can do with an integration with a CMMS system. So it's quite important to have a good device management to go through the Internet of Things. Of course, we have data, so we have to analyze it, transform this data in information, so alerts, some events, or maybe some indicators. And we have some great mixing dashboard to help you to understand how an asset works, its health stats, and why it is working on this way. So here, for example, it's a mixing dashboard for an HVAC system, so the heating, ventilation, and air cooling system. And finish the use of the API to consume data from Berger-Levrault or to consume services coming from other systems like CMMS. So as we, in Berger-Levrault, we developed and market a CMMS system, which is Carousel. We have a first integration with Carousel. And when our customers are in Carousel, in the tree structure, to see all the assets that are managed at Carousel, we can, of course, in real time, see the mixing dashboard corresponding to this asset by the pairing system. We are able directly to pair some sensors, directly to some measure point in the management system, and to go through the conditional maintenance with this pairing. We are also able to launch some alarm or events directly in the CMMS and to start the process, the maintenance process in the CMMS with this triggering. Which is interesting in this alarm and these events is that the use of IoT and AI help you to have some, I would say, great qualification of the alarms. So we don't have to fix some threshold or levels for each alarm. These threshold or levels for alarm or events are automatically defined by Berger-Levrault. So why? When we use the Berger-Levrault platform with the CMMS, what can we do? Of course, we can say we are going to go through the predictive maintenance, but and to predict when a failure occurs. It's interesting to predict when a failure occurs, but it's not the main goal. The main goal is to optimize and to find the optimum. So you know that there is preventive maintenance, corrective maintenance. Preventive maintenance is quite interesting. You can have zero failure with preventive maintenance, but with a high cost of maintenance. With corrective maintenance, it's a low cost, but when a failure occurs, it could be very dramatic for some failures, and it could be, of course, very costly. So for each use case and for each asset, in fact, for each asset in a specific context, we will look what is the optimum of the maintenance. Okay. So it's the balance between the bad maintenance costs, the breakdowns, the security, and globally the performance of the assets. There is another interesting thing is by making correlation between the data coming from the fields, from the sensors, and the knowledge that is in the CMMS systems. We can increase the technical knowledge of the use of the assets in a specific context. And by this, we can imagine to define some maintenance plan adapted to some degradation scenarios. A quick focus on what is the process in Berger-Levrault to do this. There are three main processes. First, the monitoring. With the monitoring, we can make some auto diagnosis. With this auto diagnosis and the knowledge coming from the operation and all the data coming from the enterprise asset management or the CMMS or other management systems, we can go through prognosis. And with this prognosis and I would say the financial KPI of your maintenance activity, we can go through the help, some recommendation to help you to make decision on how to build your maintenance plan and how to manage your maintenance activity to find the optimal. To do this, there is three main techniques. The first, to make the monitoring processes and the diagnosis, is to automatically detect anomaly in the data. When we mix the data and the information coming from Bell Predict with the management system, we can go through some classification models to identify some running modes that are bad running modes, which not prevents from some degradation scenario. And with this two information, we can go from failure scenario and be able to forecast the remaining useful lifetime of your assets. To do this, we implement, that's I would say that was the big functionality of Bell Predicts, the predefined algorithms for maintenance. So we have a predefined algorithm made by our research team, and it's an agnostic algorithm to detect anomaly and to make a pre-diagnosis based on the data coming from your sensors. We can, when we detect this anomaly, we can qualify in 3 levels. This is an anomaly of the sensor, because the sensors can have anomalies. This is anomaly, it's a local anomaly, so it's an anomaly for example, only one signal. And it's a global anomaly, so in fact, it's a kind of symptom for the asset or the system. Of course, this is, as I said, an algorithm which is called Summary, that was designed by Berger-Levrault, but of course, you can use in Bell Predict some more classical statistical algorithms that are used by many method and maintenance team, like ARIMA, to detect change or anomaly in signals and in facts in the behavior of your assets. To finish on Bell Predicts, what are the field of application? So you understand that Bell Predict is not a general IoT platform, but a very dedicated IoT platform for maintenance. So Bell Predicts is well suited for facility management because it's coming with predefined configuration, tools, dashboard, and algorithm for facility management. So for wastewater, pump follow-up, for looking of the level control of meters monitoring or air conditioning system, and is also well suited for some industrial assets with some algorithms dedicated to vibration, electrical motor analysis, oil control analysis, sound detection, and the ability to detect some behavior of the assets in when it is an exploitation. Okay, so it's finished for the first part. I will go through the use of Bell Predict by Alstef, and I will do my best to give you the feedback of our staff, as Marie is not here today. So let's go for our staff group. So just to begin, as I said in the introduction, we are focused here in the maintenance and in fact, the predictive maintenance for airport baggage handling systems. Why? Because why we make this choice to deploy first in this use case. Our staff manufacture and deploy the system for the airports. When they do this, they have a lot of system constraints, on the system. The first, on the technical aspects, the more important constraint is it is entirely automated. There is no human action to decide how to transport a baggage from point A to point B in an airport's baggage handling system. Also, in the exploitation aspects, there is a very, very high service level. There is a lot of penalty if the luggage systems deliver the baggage with some delay. So when our staff sign a contract with an airport, they sign a contract with an SLA for delivering a flow of baggage, so a number of baggage in for each hour, and they have to respect it. If they not respect it, the plane is going to go with a delay, and the company is going to make some penalty on the airport for the delay, and the airport is going to distribute the penalty on all the suppliers of all the systems of the airport. Also, as our staff is the manufacturer and the deploy, and as I said, they also market services like maintenance services for the airport baggage handling systems. They are very interested on making new business models to sell to the airports higher SLA, but also to sell them the ability to make predictive maintenance on the baggage handling systems. How to do this? We make a partnership with our customer, and we decide to make a good deal. The customer help us to define in a very pragmatic way BL predicts, and we deliver them a BL predicts as an OEM solution to help us to define a new offer, which is called Bag Expert. I will talk about Bag Expert at the end. And this offer will be market by our staff to their customers. One specific thing in this context is that airport baggage handling system is made with there is a very complex automation, but the assets are quite simple. Or the majority of the assets of the airport baggage handling systems are conveyor. So a conveyor is a very simple system. Regarding to six-axis robots, is very simple. And it's not very costly. So each conveyor is not very costly. So we have to make this with a very contained budget. We cannot deploy some very expensive technology. The two equipment that we consider in this project are the carousel and the conveyor. The conveyor are mainly in the I would say in the factory of the airport. So when we are a user, or when we go to the airport, we never see the conveyor, but we see the carousel where we go to get our luggage at the end of the flight. So we are interested in the two systems. There is some difference between the conveyor and the carousel. The main is that the conveyor is very simple and there is a lot of repetition of conveyors, same conveyors in the luggage system. Carousel are more complicated as they are bigger. There is a higher mechanical sensibility because there is a driving chain, many rollers, many moving parts, and also they are visible from the customers of the airports. So it's very important that there is no noise. How is it noise? The conveyor, the carousel must not be noisy, and no failure. To do this, the first step is to collect the data. How to collect the data? Alstef makes some choice. The choice was made by with our support, but is the technology used in the IoT field to collect the data was made by our customers, and they made it regarding two main requirements. Three, in fact. The security. So the security is the data collection flow must be isolated from the automation flow and must be isolated from the IT system of the airport for cybersecurity reason. The costs. So as I said, we have constrained budgets, so the cost is very important. And as Alstef has more than 100 systems deployed in the world, the last main requirement is the ability to reproduce the system. To do this, this project, we made it as it's an IoT project and I would say a digital twin or the beginning of a digital twin project. We made it in the new way, a new way for the digital projects. First, we must sense and understand. And after that, we must try on one example. When we try, we must run it on the field on one example, on one prototype. And when this prototype prove the efficiency on the field, we can go and run to scale. So you have here the planning and the dates and the main steps of this project. What is important, it's iterative. It's iterative, and we try to make some quick learn on the project. But even if it's iterative and we try to have quick learns, it's a long-term project. And in this long-term projects, we need to have the ability to adapt to some technological change, but also economical context, but also other kind of context like COVID context. Okay, so the technology that we use at the first step in now 3 years ago was not the same, but the technology we deploy today in the airports when Alstef go on the scale. So now I will take some less than 10 minutes to show you quickly some example that what Alstef get, what Alstef learn by using this IoT platform and by using this kind of approach for maintenance 4.0. In fact, what you see here is the choice to link directly the maintenance and the operation. So Alstef consider with this project that maintenance and operation must work together. And they build So with Bell Predict, we've built, by data modeling, of course, and data science, some new maintenance indicators. And these maintenance indicators, as you can see, are built on operating indicators. So for example, they are now able to make the conditional maintenance not directly on some sensors, but on some operating indicators, like, for example, the operating time, the effective operating time of the assets, but also on the energy consumption of the assets. So it's a kind of quick learn of the project. What you can see also in this graph, in the first graph on the left, is that there is a huge difference between operating time between conveyors, between 1 to 10. Before this project, Alstef was doing systematic maintenance on all the conveyors. So every 6 months, they do the same operating maintenance plan for all the conveyors. With this kind of analysis, we change our strategy. Another quick learn is the use of the anomaly detection on the data. So by only on the intensity, electrical intensity of the electrical motor for the conveyor or carousel and the speed of the belt, we combine these two measures. We run the algorithm for anomaly detection, and here we can see that there is a lot of anomaly coming from operation, baggage that are blocked, baggage jam, baggage that are inject very violently on the conveyor. And what we can see is that the overload coming from the operation is due to the automation process, in fact. This overload, has an impact on how the assets operate and are used, and reduce, in fact, the useful lifetime of this conveyor. For example, a lot of jam. The consequence is a lot of baggage injection, stop and go, stop and go, stop and go. And this repetition of stop and go is not very good for the conveyor. Another example, we try to estimate the number of baggage transports by each conveyor. It is too costly to deploy control sensor on each conveyor, so we build an EA model to estimate this. And what is interesting is the ability to build a new indicator, that is the cost energy used for each baggage. And with this cost energy, when this cost energy is, if we look at the drifts, we can adjust the maintenance plan to reduce the cost of energy for each baggage. On our case, here we try to estimate the number of baggage which is loaded in carousel. In the theory, for each carousel, so where people get to take their baggage after the flight, the automation is made to have on max 25 baggage. As you can see on the graph, we are regularly exceeded the 25 baggage. The impact of this is on the bag injection upstream, which is going to have some phases of, how to say, very choppy operation. Okay, so stop and go, stop and go, stop and go, which is not very good and have a bad impact on the remaining useful lifetime. So here I show you some new operation indicators. Now, how to detect breakdowns. Many things. The main things is that to detect breakdowns, we have to see the drifts. And to see the drift, we have to do it in comparable condition on the operation. So we can only do it in a luggage system when the conveyor is running empty. Because when it's running with some luggage, there is a high variability due to different weights and tip of the luggage. So we work on to neutralize this variability. We do this with the intensity and speed, but also we do this with the temperature of the motor and the oil. In the first step, we try to do this by engineering. And by the engineering is the top, the graph on the right on the top. We do not detect any specific signature for anomaly or failures regarding to the temperature. By using automated algorithms on the graph that is down, we detect that there is a signature linked to the stabilization of the temperature and the gradient of the temperature at standstill after a workload. So we build a new indicator based on this, and we can have a look on the drift of this indicator. And by having a look on the drift of this indicator, we are able to detect two kinds of new problems and to prevent them: the ventilation failure for the electrical motor and some problem with the belts of the conveyor. To finish, last use case or insights, of course, with all these raw data models, synthetic indicators, we have a part of a digital twin. So we are able, with this part of digital twin, to make some simulation. And here, we try to simulate two operations to automation mode for the same conveyor. On the left, you can see an automation which is running for a specific time. So each time a luggage is coming, we run for 5 minutes and stop. And on the right, another automation mode, which is called wave concept. So when there is no luggage, so the conveyor is coming up and down regarding to the placement of the luggage. And there is a lot of stop and go, and we can prove that we can save 2x energy by changing the automation. To finish, the main benefits for Alstef, in fact, is the long-term benefits. So there is a quick win, some quick wins. I'm not going to comment all the quick wins, but the long-term approach can help them to adjust the preventive maintenance and preserve a lot of money, and also to improve the conception of conveyor and carousel. Thank you. If you have any question, I'm going to look online, and there is some question. No question online? No? Okay. So thank you very much. Have a good